When a UFO was spotted in 1957, the US Air Force measured all the frequencies coming from the craft, but didn't know what they meant. And at exactly the same time, a brilliant young physicist called Frederick Alzofon was sharing a paper that he was writing with Richard Feynman. His paper discussed a new way of looking at the electromagnetic universe and a new way of how matter interacts with gravity. This is the story of the UFO and the physicist. How the US Air Force had recorded the frequencies of the flying saucer, but didn't know how it worked. And how a brilliant physicist had a great idea about how gravity modification might work, but he didn't know about the UFO. The serendipity of the UFO and the physicist coming together is one of the best stories ever told.
This occurred in 1960. My dad had just published a paper on the origin of the gravitational force.
Right.
And this was, the Air Force was very interested in worldwide research in gravitation. And they commissioned a study by a PhD physicist in San Francisco by the name of Dr. Maurice Garbel, who I'm sure has passed on by this time. I did get to meet him when I was about 10 years old. But he surveyed everything in every country, including the Soviet Union, to see if anybody had any plausible way of interfering with the force of gravity. When he came to my father's theory, he said, this one looks like it could be used. And he wondered if my dad had done any thinking about that. That was in 1960, and my dad had no idea how to turn it into technology. Right. However, Garbel contacted the Air Force and he said, well, here's a homegrown physicist who might have the answer. And so this resulted in a meeting at the Foreign Technology wing of Ames Research Center.
Ames, right.
Yeah, at Moffett Field. My dad was working at Moffett Field at the time. In fact, he had worked at Ames.
Right.
So it was a collegial kind of a thing to set up. And he walked into the meeting hoping, against hope, that they would fund a research project. And in fact, they said, yes, we'll fund your research. But how soon can you get us something that flies?
Yeah, we want.
And he said, well, I don't know. This is research. And he's accustomed to thinking of research as an open-ended inquiry, but they were strictly interested in technology immediately, or not as soon as possible. And he refused to give them a date. And then there was another bug in the conversation, and that was, Dr. Alzofon, we're going to have to classify your project higher than the Manhattan Project. And my dad had actually come in contact with the Manhattan Project during World War II. He'd had a heart murmur, so they 4F'd him, and he was working at the cyclotron, and he was well aware of the kind of secrecy, what secrecy did to science. So he didn't want to participate in it. And he also suspected at this point that the only purpose they had in funding his research was to turn it into something that could drop bombs on the other side, or just explosives, was a drone going over there and blowing itself up. He didn't want it for that. He wanted to throw open the space frontier. And by the way, he had been telling me that since I was 8 years old.
Oh, great.
And he predicted what has gone on with SpaceX and the other private enterprise attempts to get into space. They're facing the same barrier that rocketry was facing back in the 50s, and that is
new. No.
Yeah, you got to spend so much fuel getting out into space, you have practically nothing left over to maneuver out there. And gravity control solves all of that. So he was looking for gravity control at least from 1958.
And for the benefit of mankind. I mean, I think that comes very much across in your and your dad's work.
that he was completely consistent on that. He did,
Yeah.
for example, he got another offer for unlimited funding from a certain alphabet agency
Hmm.
and a very shady character who called him on the phone. And this guy was raving drunk, and he wanted to know, how come those UFOs are so heavy? It doesn't make any sense. How do they fly around when they're so freaking heavy?
Hmm.
And my dad gave him an answer immediately. And this guy was so impressed that he counteroffered immediately unlimited funding. He said, I can get you any amount of money. So my dad said, okay, well, I'll think about it. So he contacted somebody who knew about this guy and then quickly
Yeah.
decided, no, I don't want anything to do with that agency. And he was always dedicated to getting this out there for humanity. And
Oh,
that's the
yeah.
reason he turned down the money.
As soon as I read Frederick Alzofon's ideas, it really rang a bell with me. Let me tell you a story and tell you why. We have a family friend whose father worked with Ernest Rutherford at the Cavendish Laboratory in Cambridge. The idea of the atom was a meatball, a plum pudding, but Ernest Rutherford did the gold foil experiment. He fired alpha particles through solid gold metal and discovered that nothing is there. Atoms are charges. There's nothing solid in an atom. It's just bonds between electromagnetic forces. So how does gravity really work? The only thing inside an atom are charges. Gravity must affect the electromagnetic charges inside atomic material.
Einstein had been around a long time by the time I was born. So the issue was that Einstein had been very successful at predicting gravitation and the behavior of light around stars. And his model was a mathematical model.
Right.
The space-time curvature caused gravitation in his model.
Mm-hmm.
However, my dad went back further to pre-Einstein thinking about electromagnetism to come up with his theory, which, by the way, is simply a modification of the special theory of relativity. In other words, he didn't disagree with Einstein. He just thought the general theory of relativity was going down the wrong route to, and it's especially because of what you just said about everything being electromagnetism. It stands to reason that gravitation was was part of this spectrum, the electromagnetic effects, and he found the link of it eventually, but it took a long time.
So everything in the big world, the world of atoms, is made up of millions of individual atoms, all spinning in random directions. If only we could orientate and align all those spins, we might be able to understand how matter is affected by gravity. Mark and Sharon, you very much came up with dynamic nuclear orientation. I think those three words. It's just fantastic.
Yes, that was actually that came out of Frederick Alzofon, and David was actually part of the help with the discovery. David actually introduced his father to the RB-47 incident with this book by James McCampbell.
Oh yeah, that one.
Yeah, so on page like 108 of this book, it describes it. David, you want to tell the story over?
Oh, I'd love to tell the story. It was a sheer coincidence. There was a kind of bohemian bookstore in Menlo Park, and I walked in there one day and I saw that book on the bookshelf. And I opened it up and I thought, wow, my dad's going to be interested in this.
Right.
And so in scanning through it, I saw the story about the RB-47, the electronic countermeasures training mission, and and what happened, and all of those numbers.
Yeah.
And so I sent it to him. And about 2 months later, he said, I think I know what they're doing. But he had to go to a technical library down south and just scan the bookshelves. And that's when he found a book called Here it is.
He didn't just find it.
No,
Yeah,
look,
it
you
fell off
both.
the bookshelf. That's the weird thing. He said it was almost supernatural what happened because this book popped off the bookshelf and fell at his feet. And he picked it up and looked at it and said, "This is the book I want."
Mm.
And
Right,
it was
right.
about dynamic nuclear orientation.
Ah, right. That was it.
You could buy yourself a copy on Amazon for $5,000 used.
Ooh, yeah. I'll get.
Great deal.
All right.
So Mark and Jared at Falcon Aerospace have very much picked up the beacon of David Alzofon. They wanted to repeat David's father's experiment. But does it work?
Orienting subatomic spin is the goal, and orienting subatomic spin is anti-gravity. Now, I say this as a big statement. I'll show you how we came to that conclusion.
Yeah.
So this is the first paper ever written on subatomic spin, 1953 by Albert Overhauser.
Okay.
Albert W. Overhauser. And he mentions over here, and I highlighted it, that the as they bring the temperature down on the samples, the spin relaxation time increases because temperature is knocking these oriented spins out of alignment. So you have a thermal equilibrium. But even when they reached near 0 degrees Kelvin,
Yeah.
the math didn't add up anymore. Something else was perturbing the samples and knocking them out around 100 times faster than the predicted value.
The relaxed.
Now,
right.
Yeah, the relaxed value was happening 100 times faster. Now, Fred saw this and said, what's happening here is gravity is interacting with it. It's the only thing interacting with it right now. This is gravity interacting with it, which is why we have the term anti-gravity. Because if you're maintaining a state of this I like to call it a house of cards. It's highly oriented. It's not a high energy state. It's highly oriented. It's highly organized. If you're maintaining a state that gravity can't interact with, and it needs to fight it to get it into this disoriented state in order to interact with it, gravity is doing work. And
or something's doing work, and that something was visible by Frederick. Yeah.
Something is doing work on the sample in order to disorient it. So if gravity is doing work on it, it stands to reason that the gravitational attraction to that sample would drop to that degree.
In a rare behind-the-scenes visit, last year Tim Ventura visited Falcon Aerospace, and Mark showed him the machine that he's using to investigate anti-gravity.
The device behind me really got a tribute to this to the great George Hathaway. He, together with Daniel Alzofon, built this machine, and it's a real tragedy. They spent so much effort building it, but they never got around to running the actual test on the sample of their choosing, which was ruby, which we'll get into later. I don't think it was the best choice, but regardless, the machine is set up for rapid testing of multiple samples, and unfortunately they never even ran a single sample through it. They ran out of money and out of interest apparently at the last moment, right when the thing was pretty much ready to go. And it sat dormant for many years. George recently reached out to me asking if I would like to come and pick it up because he saw the work I was doing on the X-band version of this, X-band being like 8 to 12 gigahertz, so higher frequency, higher magnetic field strength. But I always believed deep down that the lower frequencies and lower field strengths would yield better results because at the lower frequencies the energy can penetrate the sample better. Also, the equipment's a lot cheaper at lower frequencies, and it's easier to, much larger spaces. You can put in larger samples. You can the sample shape detunes the chamber less. There's a lot of factors that go in favor of a lower frequency, lower field strength experiment, indicating a better coupling that would happen at those levels. So what this is an S-band, or roughly 3 gigahertz setup, and they went to extreme lengths to provide to make sure that the experiment will yield accurate results. They included cryogenic capability. This thing can go down to liquid helium temperatures, which is amazing. That's extremely difficult to achieve. The piping and all the hardware for the cryogenics is on the other side of it. You can't. It's out of screenshot here. Over here, you can see there's also a vacuum chamber. So this is done at vacuum in cryogenic environment with an S-band inside of an S-band waveguide. So the amount of moving parts in this setup is astounding. And we're very excited to see what it can do. It should be pretty easy to mount samples onto it and push them into the chamber, pull a vacuum, and we'll be able to run it at cryogenic if we like, liquid helium or liquid nitrogen. Liquid helium is pretty expensive right now. And hopefully we'd be able to discern which samples and what metamaterials are necessary to maximize this effect.
We're looking for qualitative, quantitative, actually, we're trying to get actual numbers and figure out how to improve on this effect and what methods would work best, what frequencies, what magnetic field strengths, right, and so on and so forth. We've seen various effects with this experiment, which is why we're continuing with it. It's a very finicky system to run.
Right.
And that's why we have Jared Yates over here as an RF engineer, and he's signed a couple of NDAs with different agencies, and he's been able to help me fine tune all the RF components and such.
So let's just talk about spin, just generally, centrifugal forces. I mean, so when something spins, yay! I know. I think a fidget spinner, I've got one as well in my hand, is a really good thing to have, because you start learning things as a kid and with a gyroscope, go like this, and you've got a force. Yeah, you've got force. Talk to me. What is spin precession and vector movement? Who's going to tackle that?
I'll tackle that.
Thank you.
So subatomic particles are electromagnetic energy spun in on itself. When you got something spinning, you got a gyroscope. So, and a gyroscope is free to move along its plane and along its axes without any restriction. Mm-hmm. Try to change that and you get a torque 90 degrees if you try to change the orientation of spin. Subatomic particles are wobbling around in many different directions simultaneously.
Right.
Their spin is completely incoherent. Now, when you move something that's wobbling around, through space, if you were to accelerate it, what you would do is change the wobbles of the subatomic particles. So when you take a ball and you throw it, mm-hmm, and you impart 5 joules of energy, let's say, into that ball, that 5 joules of energy is being stored in the ball in the form of momentum, as in changes in the wobbles of subatomic particles. That's where inertia comes from. Inertia comes from subatomic particle wobble changes.
The wobble changes. It makes
the wobble
sense.
Changes.
Yeah.
And
you can demonstrate that in the big world, in the far field world with a spinning top, or I gave the example of Eric Lathwaite with his spinning discs. Gyroscopes. Mm-hmm.
Now, to get rid of that effect, all you got to do is orient the subatomic particle spins, and then suddenly the craft is free to move along its plane and its axis without any restriction. But the one thing it can't do, and we've never seen them do it, is a barrel roll. Nobody ever sees UFOs do barrel rolls.
There's probably one important caveat that we should clear up here, because otherwise the internet will eat us alive. So this is physical spin. When we're talking about subatomic spins, we're not talking about this. This is
we don't know that.
Okay,
you can't see it, right?
You can't see it, and most of the time, people are using quantum mechanics to describe that spin at that size. And because space-time gets really wonky as you get smaller and smaller and smaller, most people just describe it as like this intrinsic angular momentum. So the edge of this thing has some momentum because it's spinning around. But when you get down to the subatomic size, and space-time is all crunched up and weird and quantum foamy, They just say, forget about all the physical movement and stuff. We'll just say it's got that amount of momentum, but we don't know like just how much that is, right? We'll just quantize that. As far as actually being able to change some of the RF parameters, be able to induce thrust in more in one way and less in the other way. The setup that we have going on there at Falcon Space, you can increase or decrease the amount of the effect that you're seeing based upon tweaking some of the different parameters around there. So if the occupants of the craft wanted to increase the thrust on the back end and decrease the thrust on the front end just a little bit to make it rotate like that, right? It'll start doing that.
Right.
The fact that you see them wobbling around is probably indicative, like Mark was getting at, is probably indicative of how there is a signal that is being processed around as this thing is going. So there's a beat frequency in that RV-57, the radar airplane that saw it. They saw a 2.995 to 3 gigahertz signal with a 600 hertz beat frequency in there.
But guys, you're sitting in a laboratory, you've got tools. And so when you turned it all on and took Frederick and your own ideas, I want to talk about that steppiness in a minute, does it work? I mean, are you seeing an effect, and what are you seeing?
So far, what we have seen an effect. And you can see this is several repetitions of an experiment where the magnetic field was being swept and the weight was being measured. And we saw a consistent drop, like changes in weight, even these little ripples over here.
Yeah.
They were quite consistent. And then there's this massive drop over here. This only happened in a field that had a slight inhomogeneity, meaning that it was stronger in one side and weaker in the other by a very small amount. When the field was perfectly homogeneous, we didn't see these kind of effects, not yet. So which would indicate that it's possible to use this effect to not only make matter weightless, but also direct where it will go.
Yeah.
Because if you make it 1,000 Gauss on top and 1,100 on the bottom of the craft, you're going up.
So the way that the whole thing is working is you have a magnet on top and a magnet on bottom. And so you're creating a uniform magnetic field in one direction.
Yeah.
And that magnetic field is causing your sample to magnetize in a certain way, right? It's in that magnetic field.
Sure.
So while that thing is at a very specific magnetic field strength, it needs to get hit with a very specific RF frequency. And that RF frequency is causing all of these little electron clouds around them to spin up like a gyroscope.
Right.
So if you have that magnetic field strength either too strong or too weak, it'll mess with all those electrons. So it needs to be just right. So with Mark's setup there, he has very, very precise control on that magnetic field strength. Right. So before you even start doing any of your testing, you need to identify for every different kind of element or every different kind of sample you're going to test, you need to characterize it, and you need to figure out exactly what frequency of RF you need to hit it with to make all of those electron clouds around the atoms. So for his setup there, with the magnetic field strength, as that magnetic field strength changes as he's stepping through and doing the sweep, it slightly changes the RF frequency as well, very little bit. So it becomes this whole balancing game. Like he said, a house of cards, I think of it like a bunch of spinning plates.
Okay,
like you're stacked atop each other, right? Because as you change one variable, it's changing the other variables, which are changing the first. Very nonlinear.
What Jared is talking about is the Overhauser effect. So when Overhauser discovered this effect, he also discovered something interesting. What Jared just described, that as you apply dynamic nuclear polarization to the sample, your gyromagnetic ratio, which is the amount of magnetic field for your set frequency necessary to reach this resonance, goes down. Now, the reason why he describes what's happening is, so magnetism is spin orientation of electrons. What we're doing over here, dynamic nuclear polarization, is spin orientation of subatomic particles, another form of magnetism. Now, what happens is, as you orient subatomic particles, they create their own form of electromagnetism,
Right.
changing the B field. So now the kernel, the core of the atom, now it's producing 100 Gauss.
Right.
Instead of 1,000 Gauss, you need 900. Now it's producing 200. Instead of 1,000 Gauss, you need 800 external. And it keeps on dropping the amount of magnetic field necessary external in order to keep this effect going. So you need to sweep the magnetic field downward as the DNO builds up in the core. Therefore, if this subatomic magnetism is actually anti-gravity, and you have a craft that is covered in this effect, like a skin effect on the surface, everything inside of it, whether it's solid osmium or gaseous helium, would be affected.
Or the pilot.
The pilot,
Yes.
and everything else.
Right.
And it's also useful to use the surface of the craft for this effect, and also use it for radiation shielding. So you can have all of your RF stuff happening outside, and the pilot and the crew will be inside the craft shielded, and then any human occupant that may come by and start wondering what's going on will end up getting an RF burn, which is what happens.
Which we've seen. Absolutely.
which is why we have these custom-made silver-lined hoodies over here to protect us from the silver-lined hoodies. We don't do tinfoil. We don't screw around with tinfoil.
No. Tinfoil's crap. You need to go silver.
Yeah.
So if you were sitting inside one of these craft and they were displaying G-forces of a tremendous acceleration, enough to turn a blobby bag of water like a human into Jello, would you not have those G-forces on you if you were inside the skin of a craft? Would you be protected from extreme G?
To the degree that DNO was achieved. If you're at 100%, you won't feel anything. If you're at 90%, you'll feel it, divided by 10.
Okay, so you want the safe level before you go zooming around and chasing the F-15. All right, okay, good. All right.
Well, maybe you don't want to turn it up to 100, because then you don't get a feel for the thing. You want to keep it
Oh,
like
yeah. You want some feedback.
You want to feel something.
Yeah,
you want
exactly.
some feedback. Yeah.
It's a bit like Tim in my electric car. We definitely want road holding.
The big question that came to my mind: are modern defense contractors exploring the same effect?
They already are. I actually went to Alien Con in 2019 in Los Angeles, and there was a panel of people up there, including some from the military industrial complex. And I came there in my lab coat, and they shut down the Q&A as it was my turn. But I still managed to ask them all a question. They were all curious and I asked them about the Alzofon experiment. And one of the guys from the DoD motioned for me to follow him, and I followed him to the secret area where it's only the presenters go. He told me, yes, we worked on that. The results are classified.
Oh, well done for not classifying your results.
We're doing the exact opposite. It's open source.
Right.
May I venture an opinion about the military?
Please
what
do,
they've
David.
been doing and why?
Yeah.
Okay. I think that the Roswell recovery story is true. And
Okay.
I think they were working on reverse engineering the propulsion system long before my dad came out with his paper. But I think that's why in 1960, they wanted to know how he would instrument the gravity control effect. When he came out with his 1981 paper, he gave it away completely. He didn't intend to do that.
Right.
And that's another long story about the patent office and so forth. But I think that the military ran with it at that point, because they had been able to reverse the engineered propulsion to the point where they had these bell-shaped saucer vehicles that would hop like that.
Right.
But they didn't have a saucer that could take them into space. And I think that they didn't understand the general principles of physics behind the drive. They're just imitating what the data told them to do. It was like an instruction book on how to get this effect, but they didn't know why it was happening because it was contradicting everything that Einstein said in the general theory of relativity.
Now, there's good evidence that people have actually retrieved material from crashed UFOs. If these strange layered metals are really from UFOs, the question is, how did they work in the anti-gravity device?
Jared, what's your thoughts on a connection between arts parts or these UFO crashes and this Alzofon experiment with dynamic nuclear polarization?
And was it a part of the skin of the craft, do you think?
Yes.
The quick background on Art's parts is in 1947, one of the first guys to the White Sands missile range crash site, he reached up and he grabbed some pieces from the center underside of the craft, shoved it in his pocket, didn't say a word until 1974. When he was on his deathbed, he gives it to his grandson. Grandson holds on to it until 1996, gives it to Linda Moulton Howe and Art Bell. From that point on, it goes to a bunch of different scientists to get tested. Eventually, in late June of 2024, a tiny little piece of that falls into Mark's hands.
I've seen it.
Yep. So since then, we've been doing a lot of tests on it. We've been identifying stuff at the atomic level on this thing.
Okay.
There's a lot of there. As far as how much it relates to the Alzofon experiment, we have high hopes that we're going to be able to test it here in the near future, within the next few months, hopefully. We're going to be able to test it inside that chamber right behind Mark there. The difficult part is because it's so small. It's 2 millimeters by 4 millimeters. Very, very small piece. Very, very light. It's like 7 milligrams with the glue. So in order to identify the effect in there, we're going to have to up our game a little bit more on our sensitivity on our scale there. It's already sensitive enough, but you want to get rid of the noise. And every time a truck drives by, the whole scale goes.
I bet. Yeah. There's the scale. Fantastic.
Yep.
Right.
So that sample is made up of layered materials, and it's possible that there could be some interactions with the layered magnesium, zinc, and bismuth that at very specific magnetic field strengths and RF frequencies, you might be able to get some Alzofon effect coming out of it. That said, bismuth is a very, very interesting and unique element when it comes to magnetic fields.
Right.
It doesn't respond the way normal stuff responds. And there's actually some very unique stuff about the thickness of these bismuth layers, where at those thicknesses, very, very interesting things happen. The way that it repels magnetic fields, the intensity of that goes up tremendously at those very, very small thicknesses. So we'll probably have to end up getting some cryogenics and some better resolution on our setup there. But I mean, we have the will, so there is surely a way.
Thank you so much, everybody, and a big shout out to Tim Ventura for making this happen. I and you need to keep in touch with what Falcon Space are up to. If they can master gravity modification, it will change humanity. The truth is out there.